Can anybody hear me now? Hey, there's Jeff.
Yeah, yes, we can hear you now.
Okay.
Yes, we can hear you. Good morning, everybody. Sorry, we are starting late today. We're going to be talking about the use of recycled concrete, aggregate in concrete. And this is in continuation of our ongoing research phase of webinars, which we do every month. And those who are hooking up for the first time, we'll let you know how you can be continuously hooked up to our monthly presentations. So our topic today is of interest to us. It was from this Office of Materials and Road Research, our concrete research section, that we developed the mathematical method for quantifying the enhancement of the interfacial transition zone in concrete called the aggregate avoidance index method. And we developed that from our internal research in recycled concrete aggregate in concrete. Today, going further, we're going to have a presentation from Professor Farhad Reza from Minnesota State University, Mankato, where he is a professor in the civil and mechanical engineering department. He has been in that faculty for about 9 years now. And prior to that, he was at Ohio Northern University, and that was for 8 years. He obtained his BSc in civil engineering from University of Iowa, and he got his master's and PhD from Clarkson University in New York. Now, Dr. Reza's research interests include concrete materials science, pavement performance modeling, and non-destructive testing. He is also a registered professional engineer in the states of, I believe, Minnesota, Ohio, and New York. Correct me if I'm wrong. All right, so make welcome Professor Farhad Reza.
Yeah, you can try talking.
Good morning. Can you guys hear me?
We can hear you fine.
Okay, good.
Yes.
Yeah. Okay, so good morning, everyone. Thanks for inviting me up here today to talk to you guys. So I want to talk today about the sustainability of using recycled concrete aggregate in concrete pavements. And the majority of this talk is based on a previous talk that we did at the TRB conference in 2018. And Bernard and Dr. James Wild were also my co-authors on that. So as you know, sustainability is, it's at the forefront of everything that we do nowadays. And a definition of sustainability, for example, you can see from the Federal Highway Administration, the INVEST program, which is a method for rating sustainability of transportation projects. So the goal of sustainability is satisfaction of basic social and economic needs, both present and future, and the responsible use of natural resources. Also, for those of us who are civil engineers, the American Society of Civil Engineers Code of Ethics, the fundamental canon number 1, says that engineers shall hold paramount the safety, health, and welfare of the public. And the second statement there is shall strive to comply with the principles of sustainable development. So it's an important topic for us. Then ASC also gives some guidance about what does it mean. So as an engineer, if you want to consider sustainability, what are the steps that you should be considering? So they gave some guidelines, steps to a sustainable project. So number 1 is perform a life cycle assessment from planning all the way to removal. Avoid depletion of resources and plan for resiliency and validate the applications with some metrics or ratings. Also, the one term that's used is the triple bottom line of sustainability, which is economic, environmental, and social performance. So this term got coined in the past. Big corporations used to report basically their financial statement, so they used to report only the economic performance. But Elkington in 1998 suggested that corporations should also, in addition to the financial statements, should also be looking at environmental and social performance. So from there, this term got brought in, the triple bottom line of sustainability. So in today's talk, I'm mainly going to focus on the economic and the environmental part. So the objectives in this project here were to look at several alternatives for a realistic pavement project. And the idea was trying to get an equivalent performance between a pavement that's made with recycled concrete aggregate and a pavement that's made with conventional aggregate. So we'd evaluate the economic performance of the different alternatives using a life cycle cost analysis, and also look at the environmental performance of the different alternatives using life cycle assessment. Just to give some background about this, so in the US, we consume a lot of aggregate annually in construction. So we consume about 2 billion tons annually of aggregates. And a common estimate of how much recycled concrete is available as aggregates, it's about 5% or 100 million tons. So it could make a substantial contribution to the aggregate consumption. It's already a pretty common practice in a lot of states to use recycled concrete aggregate in the base course of pavements. For example, in a FHWA study in 2004, already 38 out of 50 states were doing that practice. So that's a common practice, but it's not that common to use it in the concrete layer itself. Back in the 1980s, across the US, there were several trial projects that were built, and Michigan had the most of them, about 30, but Minnesota was also one of the highest number of those trial projects. Subsequently, Michigan placed a moratorium on using recycled concrete aggregate in concrete in 1991 because they were observing some mid-slab cracking. Further investigations, they did further investigations later on and actually attributed it more to some design problems like inadequate joint spacing and so on, more so than the actual aggregate issues. Since that time, in the 1980s and early 1990s, there had been very few projects built in the US using recycled concrete aggregate in the pavements. But it seems like there's some renewed interest across the country in this aspect. So we can see that several recent surveys have appeared, and also several state-funded research projects seem to have appeared since around 2011 to the present time. One of the more recent constructions was at MnDOT, actually, a two-lift construction, which was performed at the Min Road facility in 2010. So with the two-lift approach, the idea is that you can use a lower quality concrete on the lower lift and then use a higher quality concrete on the top lifts. So a thicker, lower quality concrete with recycled concrete aggregates was placed on the bottom, and a thinner layer was placed on the top. Also in the Illinois tollway construction 2013, that was also a two-lift construction, and in some portions the lower lift also contains recycled concrete as well as recycled asphalt. And that's just a picture of the construction during the Min Road test facility. So you can see on the right the main the lower pavement with the recycled concrete has been poured already, and then the top layer, the second lift, is being placed on top of that. And then on the left is just a close-up picture of the exposed aggregate concrete, which was used on the top layer. Okay, so the mechanical properties of recycled concrete aggregate has a huge part to play with the performance of that concrete. So most of the literature suggests that you don't use the fines, the recycled aggregate fine material, because that causes a lot of workability issues and some durability issues with the concrete. Compressive strength of the concrete using recycled concrete, what's been reported in the literature is typically that it's about 20% lower than that if you used a natural aggregate. But if you're using a lower water cement ratio, your difference might be even more pronounced at lower water cement ratio. Because the new, Bernard mentioned about the interfacial transition zone earlier on, the aggregate already has a weaker interfacial transition zone than the new concrete. So this could lead to a bigger difference in your compressive strengths when you have lower water cement ratios. And flexural strengths have been typically reported to be about 10% lower. Modulus of elasticity of the concrete's about 20 to 40% lower, and coefficient of thermal expansion is about 10 to 30% higher with the recycled concrete. On the positive side, the freeze-thaw resistance may be actually increased in using recycled concrete because you already have some entrained air within the aggregate itself. Also, when you recrush this to smaller size, decracking susceptibility may also be less. ASR potential may be higher with recycled concrete. So in general, you can see that most of the mechanical properties seem to show that recycled concrete aggregate would be performing not as well as conventional aggregate concrete. So most of the experiments and so on, most of this data were done earlier on. As I mentioned, this was done mainly in the 1980s and so on. So concrete mix designs and so on have changed quite a bit since then. So we decided to evaluate a high performance concrete mix with a relatively low water cement ratio of 0.37. For the natural aggregate, we used limestone aggregate, and cementitious content was 585 pounds per cubic yard, and we used 30% fly ash substitution. So the observed mechanical properties that we got from those experiments for 50% and 100% coarse RCA substitution, our compressive strengths were about 32% and 43% lower. If you remember, I said if you use lower water cement ratio, you would kind of expect to see more of a difference between compressive strengths. Flexural strength was about 17 to 20% lower. Drying shrinkage was 1 and 32% higher, and coefficient of thermal expansion was 1% and 11% higher. We also did some other experiments to see can we adjust the mix design such that the mechanical properties are somewhat similar. So we found some comparable properties if we lowered the water cement to 0.36 for 50% RCA, and if we lower it to 0.35 for 100% RCA. We had to increase the cement content slightly so as to keep the paste volume the same. So as we've seen, the mechanical properties in general, if you just substitute the recycled concrete aggregate for the natural coarse aggregate, in general we expect the mechanical properties to be inferior unless you make adjustments for that. So we wanted to see, does that hold true in practice? So all these pavements that were built, we had a lot of them in Minnesota that were built, in the 1980s and 90s. We wanted to look at how did they perform, look at their long-term performance record, and compare it to similar concrete pavements that were built around the same time, because we know the specifications change from time to time, so we have to keep it within the same time period. And also we looked at the same range of traffic on the pavements as well. So this is just a map showing in Minnesota the locations of those pavements with the RCA concrete. And there's about 212 miles of those pavements that were built. So we studied the different pavement performance indexes. MnDOT has a nice database. They collect annually records of ride quality, surface distress, and pavement quality, and so on. So we tracked those, as you can see on these graphs here, looking at those different indexes. This is just showing the average values of those time elapsed since construction. So looking at those indexes for both, the top one there is the recycled concrete. The bottom graph is for the conventional aggregate concrete. In both cases, we see like the ride quality index is the lower curve. So ride quality tends to deteriorate the fastest out of these indexes. A typical trigger value for major repair is like 2.5 on the ride quality index. So we can see that RQI in most cases seems to be the one that will deteriorate first and cause the trigger for major repair. Also, just to point out that towards the end, it looks like on those graphs there's a slight uptick. It's actually getting better. So the reason for that is actually that by that time some pavements have been repaired already. So the RQI, the index values are going up higher, which is causing it to look as if they're improving with time at the end. So we studied the time it took to reach for the pavements to reach a terminal RQI value of 2.5. And as we expected, in general, the RCA pavements performed a little bit worse than those pavements that were made with the natural aggregates. So based on those comparisons, the mean time to the first major concrete pavement rehabilitation was about 27 years for the RCA pavements and about 32 years for those made with natural aggregates. For the minor repairs, typically we found like by the time they get to the major CPR, most commonly they undergo 2 minor repairs along the way. And those times were fairly similar for both of them. So 16 years and 21 years for the RCA pavements, 18 years and 23 years for the natural aggregate pavements. Okay. So if you wanna, now that we know, we already hypothesized based on the mechanical properties, if you just simply substitute in the same mix design, we don't expect the RCA is gonna perform as well. So one option is to carefully control the concrete mix design such that you might get similar performance. Another option might be to actually use increased thickness to compensate for the performance. So we also looked at this. What about increasing the pavement thickness if you're going to use recycled concrete aggregate? So for this, we relied on some fatigue data. As I mentioned earlier, like there's a lot of research on the static properties, compressive strength, flexural strength, and so on. Not that much research on the dynamic or fatigue properties. So in one paper, we found that the stress level was 0.58 if you're using natural aggregates. and 0.56 for 50% RCA concrete, 0.5 for 100% RCA. And the stress level is just the maximum tensile stress that pavement's going to feel compared to the flexural strength, relative to the flexural strength of that pavement. From mechanics theory, we know that the bending stress varies inversely with the thickness squared. So if you assume a constant moment to B, B is the width of the pavement, constant M over B ratio, then you can find the theoretical required thickness increase if you want to achieve similar flexural fatigue life. So we found that for 50% RCA, you would need about a 12% increase in thickness. And for 100% RCA, that would be about a 24% increase in the pavement thickness to achieve similar fatigue lives. Okay. Moving on to some of the sustainability aspects, looking at first the economic aspects of this. Some of the past studies that were done, in Florida DOT, they did an assessment of recycled concrete versus limestone aggregates, but they were looking mainly for the use in base courses. So they found a reduced environmental impact in the processing energy and also in disposal. So the RCA was better, had a better environmental performance. As far as the costs, they found about $12.75 per ton for RCA and $13.20 for the limestone aggregates. They also assumed a 30-mile haul distance. Also, RCA was found to leach less harmful and less toxic amounts of chemicals than the limestone aggregates. Michigan DOT also performed a study, lifecycle cost analysis for RCA versus natural aggregates. If you remember, Michigan was one of those states that had the highest number of trial projects with RCA. So they found that for level 1 pavements, which they define as less than 6,000 AADT and approximately 9-inch thick, for those pavements, the cost was the same between the two types. The cost was about $15,000 on an annual worth basis. For level 3, the cost was actually less. So the economic cost was actually less for the RCA, $12,170 for the RCA versus $14,600 for the natural aggregate. So their analysis is showing a better economic value using the RCA concrete. Indiana DOT also performed a benefit cost analysis looking at recycled concrete versus natural aggregates. Some of the assumptions that they had in their analysis, they assumed $5 per ton for the RCA crushing costs, $9.50 for the natural aggregates, and 35 cents per ton per mile for the hauling cost. So using these scenarios, they came up with a net cost savings of $2.50 per ton of aggregate when they're using the RCA versus the natural aggregates. Also, with the two-lift construction, as I mentioned, that's one approach that's done in Europe, and we're starting to try that out here in the U.S. As I mentioned at Min Road, that was one of the places that we did the two-lift construction. So Texas DOT actually did a study, economic study mainly, looking at two-lift construction in the U.S. They surveyed several contractors about their process. They found that contractors would prefer to add a second batch plant, so to have like a separate batch plant for the aggregates that are going to be used in the upper lift and for the RCA for the lower lift. Also, with this type of construction, you need a second slip form paver. So the equipment cost is going to be increased, labor costs are going to be increased. However, overall, these constructions still came out cheaper compared to conventional concrete because you had a lot of savings in the material costs, and that offset the increased construction costs. So, for example, in the Minnesota construction, the conventional concrete cost about $20.38 per square yard, whereas the two-lift construction was $19.94. So it actually came out cheaper despite the increased construction costs. So in our life cycle cost analysis that we performed, this was the basic scenario. When you do LCCA, you are supposed to assume a relatively long analysis period. So we looked at 50 years for analysis period. The real discount rate we used was 1.5%, which was the recommended value from OMB. Because we're looking at the different concrete mix design, we have to actually break down the concrete mix into its components. We can't just take a lump sum value for the concrete costs. So concrete mix was broken down into its components. We realized that there's some economy of scale. So if you're doing a large project, then unit costs will be a little bit less if you do a large project. So we assumed a 7-mile long project. The old concrete pavement that was to be recycled, we assumed was 24 feet wide by 10-inch thick. And the base of the new concrete pavement to be placed was 24 feet by 8-inch. And the new concrete pavement was assumed to be 24 feet wide by 9-inch thick. For a haul distance for our analysis for the natural aggregates, we assumed 30 miles. Also, one thing to point out, when you're trying to compare different alternatives in life cycle cost analysis, you don't need to include the costs that are constant between all of the alternatives. We're just trying to look at what's the difference between these. So costs that are constant were not included. When you get to the point when you need a major concrete pavement rehabilitation, there are several techniques for the concrete pavement rehabilitation. So we had to assume one of those. So we went with diamond grinding as the major CPR technique. So for this economic analysis, we looked at 8 different alternatives. Number 1 was basically our control, conventional concrete pavement without any RCA. Based on our discussions with some MnDOT personnel and experience, again, remember those pavements in the 1980s were built with a much higher water cement ratio. Nowadays, typically, we're using much lower water cement ratios. So expectation was that these should be should be able to go a long period of time before needing a major CPR. So we assumed 59 years until the first major CPR. The next 2 had 50% coarse RCA in the concrete. The third one was including a thicker design. We said like one of the alternatives, one of the methods you can use to try and get an equivalent performance, you can make the pavement thicker. So in number 3, we had a 12% thicker design. Number 4 was also 50% coarse RCA, but here we lowered the water cement ratio to try and get equivalent performance with the conventional. Similarly, these alternatives, we had alternatives 5 through 7 were with 100% coarse RCA. Again, we had some alternatives that were looking at an increase in thickness. For example, number 6, 24% increase in thickness. Alternative 7, let's lower the water cement ratio and try and get equivalent performance. So number 7 had a lower water cement ratio. We also took a look at the economic analysis of the using the mixed designs that were used in the Min Road two-lift construction. So we also used those. We had the mixed designs available. We also looked at that in our economic analysis. So this is just showing some of the equations, relevant equations for the analysis. Again, when you're doing life cycle cost analysis, you can look at either like future costs, present costs, or on annual worth basis. That's just showing the conversions between them. The real discount rate. And if you have at the end of the analysis period, if some pavements have not yet reached the major CPR, that means they have some residual life. So remaining service life, you can take that into account as well with the residual value. Remaining service life over the expected life times the initial cost. This table just shows some of our reference data that we used during the economic analysis. So some of the things to highlight: the recycled concrete aggregate, we found the cost was about $8.75 per ton. The natural aggregate for concrete is about $22 per ton. The next one, that was the exposed aggregate that was used in the two-lift construction. And for base course, the natural aggregates price was about $16.77. Also, I mentioned like we had to break the concrete mix down, so we tried to break it into cement cost, fly ash, water, even water reducer costs as well. For the haulage, we assumed 35 cents per ton. We looked at some different options with the joint spacing as well, so we had to also include saw cut costs and dowels costs. For the two-lift construction, because of the increased labor and so on, we have a premium for the two-lift construction, which we found was $1.66 per square yard. And for major CPR, like I said, we assumed diamond grinding for major CPR, and the cost was $2.30 per square yard. Typically, when you crush old concrete pavements, you get about 40% fines from that and 60% coarse. So the amount of usable concrete aggregate was about 60% from crushing. So I mentioned like we had old concrete pavement which we assumed was crushed up. So about 60% could be used as coarse aggregate. The remaining is fines, which we're not going to be using in the mix. Typically, on a realistic project, when you crush up an old pavement, the amount of RCA that you're going to get is not going to be enough to do both the base course and the concrete pavement. And MnDOT allows up to 75% recycled RCA in the base. So in round one, we assumed that the priority was going to be given to the concrete pavement. When you crush up the old concrete, first you're going to put it in the concrete pavement. Then if anything is left over, it would be put in the base. So this was the assumption in the round one of the economic analysis. So these are the results that we got. And I just want to point out there that alternative number 7 was with 100% RCA. Number 4 was 50% RCA, and then number 1 was our conventional concrete. Number 8 was the two-lift construction. So on this economic analysis, we can see that the 100% RCA is proving to be the most economical choice. Also from this analysis, what you can see is, remember we said maybe you can increase the pavement thickness or you can try and control the mix design. It looks like controlling the mix design is the cheaper option. So those alternatives that had thicker pavements are towards the end of that table there. We searched and we found that some aggregate suppliers were actually selling, they had maybe excess stockpiles of recycled concrete aggregate. So they were actually selling this as a base aggregate at a significantly cheaper price, $5.25 per ton versus 16.77 for the natural aggregates. So when we found that, we did a second round of economic analysis where we assumed that as we said, first we assumed when you crush up the pavement, the contractor would put that in the concrete pavement. Anything left over, he would put it in the base. But now the contractor could actually purchase some extra RCA from offsite to maximize the amount of RCA in the base course as well. And MnDOT allows up to 75% RCA in the base course. So when you do this analysis where you're buying extra RCA to make the RCA content in the base up to 75%, now it favors even more. It favors the use of RCA even more. So now if we look at alternative 7 with 100% RCA compared to conventional concrete, which is number 1, you're seeing about it's almost like $5 per square yard savings using the recycled concrete aggregate. We also looked at the environmental impact of using RCA, so we did lifecycle analysis. The main tool we used there was a palette tool, which was developed, a spreadsheet-based tool, which was developed for the Recycled Material Resource Center. You input your designs for your pavements, and you specify the equipment and processes that are going to be used. And it looks at the energy consumption, water consumption, emissions, and leachate information. So this is just a comparison of, so the first one here is the mix that with 100% recycled concrete aggregate. As you can see that many quantities are calculated here, energy consumption for several different processes, emissions, for example, carbon dioxide and particulate matters and so on. And also towards the bottom, it has hazardous waste and human toxicity potential. When we compare that with conventional concrete, we found that for energy use, it's favorable for the RCA. Some of the emissions are reduced, and particularly down here, the hazardous waste generated and the human toxicity potential that's decreased when we use the RCA concrete. So in conclusions, the long-term performance of the recycled concrete, it may be worse than the natural aggregate concrete if you just use a similar mix design and you use a similar structural design. So to compensate for that, you can make some changes at the initial design phase. One option might be thicker pavements with RCA. Another option might be using lower water cement ratio and a higher cement content. The life cycle cost analysis supports the option of changing the mix design rather than increasing the thickness of the pavement. LCCA showed that it was economical to use the RCA in new concrete pavement. That turned out to be the most economical alternative. Which also makes sense because natural aggregate for concrete is usually a higher quality than the base natural aggregate. So if you can substitute, if you can use the RCA to substitute the aggregate in the concrete, it should make good economic sense to do that rather than for the base course. We found that at current rates, you can purchase extra RCA for a relatively cheap price. That makes the project even more economical. Using life cycle analysis, we showed that there's some reduced energy consumption, reduced emissions, decreased human toxicity potential for the RCA concrete. Also, another thing that we're seeing, as we said, it's pretty widespread to use RCA in the base course, but some places are reporting problems with leachate, calcium carbonate, which is called tufa, leachate when this is being used in the base course. So if you use the RCA inside the concrete, that will tend to decrease this problem because it will be encapsulated within the concrete. This research was funded by Minnesota Department of Transportation, and during the research we had to partner with several members of the National Road Research Alliance. Here. So I thank you for your time, and I guess we can have questions now. Yeah, the question. Mm-hmm. Yes, so that was the conclusion of Michigan DOT. What they said that it wasn't that much, not so much the question was whether the failures were due to structural failures or material failures. So at least with the Michigan DOT, that's what they attributed it to, that it was structural failures. And
didn't you also say that there was other variables that may skewed or influenced those results? In other words, they were going longer joint count spacing. So
right. Right. So as you mentioned, like in the Michigan case, they had too long of a joint spacing, which may have caused that problem rather than But with the Minnesota performance, we've seen relatively good performance. Some of those that were built in the 80s and 90s, they're still in service. I think, in fact, all of them, almost all of them, are still in service. So in the Minnesota case, we found that construction was fairly similar. So in this case, it's probably due to material. The performance being slightly worse is due to the material properties for that. Yeah. Okay, so as I said, what we found was it seems to be the ride quality that's deteriorating the most. So the more than surface distress, we found that ride quality seemed to be the triggering factor for that. Yeah.
I don't see any questions online.
Are there any questions online?
Does not look like it.
Another round of applause for Professor Reza. And I just wanted to announce that the next research pays off seminar is on April 17th, and that will be chip seal program in Oregon. It will be rendered by Ashley Boss of Iowa State University. And sequel to that, you will have May 18th, development of energy cost and environmental based life cycle tool for in-place recycling methods. We have gone sustainable. This is a sustainability program here. And that will be by Hassan Oza and Imad Akwadi of the Civil Engineering Department, University of Illinois, Urbana-Champaign. So make sure that you are signed on for that and that you are in the continuous sign-on. There's a recurring sign-on that can happen if we send you the link. I hope everybody has that. So we look forward to having you in the next and the subsequent research pays off. Once again, thank you very much, and thank you for accommodating our late start. And thank you again to Professor Reza. Thanks.